Control rooms went quiet, then suddenly changed everything. Cameras around Mars stopped staring at dust and rock. New commands rushed out across millions of kilometers. A target from outside our solar system was cutting through the dark, and it was heading past Mars with no intention of slowing down. Nobody could ask it to wait. Nobody could send a mission to chase it. For a few brief days, humanity had one chance to look at a visitor from another star. And what those machines saw would raise a question we still cannot answer completely. At first, the object did not look like history. It looked small, faint, and easy to ignore, the kind of dim blur sky surveys catch all the time. But the moment astronomers traced its path, the story changed. This thing was not orbiting the sun the way ordinary comets do. It was not a member of our solar system that had drifted inward from some distant icy cloud. It was just passing through. It had come from somewhere else, somewhere beyond the family of worlds that formed with our sun. It was later named 3I/Atlas, and that simple label hid something astonishing. It was only the third confirmed interstellar object ever seen by humanity. That matters more than it sounds. Think about how many nights human beings have spent looking up. Think about centuries of maps, telescopes, observatories, and now giant machines in orbit and on other planets. In all that time, we had only confirmed 2 true outsiders before this one. First came Oumuamua in 2017, strange and still debated. Then came Borisov in 2019, more comet-like and easier to understand. Then, in 2025, came the third visitor, and this one arrived with a gift the others did not. It was going to pass close enough to Mars that the spacecraft already there could try to watch it. That was the moment the story stopped being just another astronomy update. Now it was a race. The first report came on July 1st, 2025, when the ATLAS survey telescope in Rio Hurtado, Chile, sent observations to the minor planet center. Soon after, astronomers checked older images and found earlier sightings reaching back into June. That is often how these discoveries work. First the object appears, then the archives speak, then the math begins. And the math told everyone the same thing. This was not a local comet on a long loop. This was a genuine intruder from interstellar space. You can almost feel the mood in those first days. Excitement, yes, but also pressure. Because interstellar objects do not give second chances, they do not settle into neat return paths that let us study them again next year. They appear, they cross our sky, and they leave forever. If you miss the good observing window, the story is over. By the time the world fully understood what 3I/Atlas was, teams were already trying to answer a harder question. How much could we learn before it vanished? That is where Mars entered the picture. Its path through the inner solar system was extraordinary for one simple reason. On October 3rd, it would pass Mars at about 29 million kilometers. In everyday life, that sounds impossibly far. In space science, for an interstellar object, it is a close brush. Close enough to tempt mission planners into something nobody had ever done before. Instead of watching from Earth alone, they could ask spacecraft at Mars to turn and look outward into space. Not at the planet beneath them, not at craters, clouds, or dust storms, at a traveler from another star. If you were sitting in one of those mission rooms, what would you have thought in the moment? Would you have played it safe and kept your instruments on their usual targets? Or would you have taken the risk and pointed them into the dark for a chance that might never come again? Because that was the choice. Every observation comes with a cost. Time on a spacecraft is precious. Power is limited. Schedules are packed. And these machines were not built for this job. The European Space Agency moved first with some of the clearest public detail. Between October 1st and October 7th, ExoMars Trace Gas Orbiter and Mars Express turned their eyes toward the comet. Both had the best view of any ESA spacecraft. Their closest moment came during that October 3rd passage, when the comet was about 30 million kilometers away. Even then, this was not easy. These cameras were made to image bright terrain on Mars, not a dim target in deep space. One instrument on ExoMars, the Color and Stereo Surface Imaging System, had to chase a faint smudge far from its normal kind of work. Scientists openly admitted they did not know how well it would go. That honesty is important. Space missions look smooth when the pictures finally appear online. But before those images arrive, there's always doubt. Would the target be too dim? Would the motion blur ruin the shot? Would the exposure be wrong? Would the whole attempt produce nothing but noise? Mars Express struggled more because its maximum exposure time was shorter. ExoMars Trace Gas Orbiter did better, catching a fuzzy white dot sliding against the star field. The nucleus itself could not be separated from the coma, the cloud of gas and dust around it, but the comet was there, real, measured, seen from Mars. Pause on that for a second. A machine built by humans, sent to another world, looked away from that world and photographed an object that was born around some other star. That is not a line from science fiction. That happened. And Mars was not the only witness. NASA missions joined the hunt too. Orbiters around Mars and instruments across the agency's wider fleet helped track the visitor as it came in and later as it headed out. Hubble watched it. Webb studied it. Other missions added pieces. Ground telescopes across Earth followed the same target. Suddenly, this was not one telescope's discovery. It was a coordinated pursuit across space. That is where the mystery deepened. The first images were thrilling, but they did not tell the whole story. A dot can prove an object is there. It cannot tell you what kind of ancient place made it. It cannot tell you how long it wandered the galaxy. It cannot tell you why this one looked so active, or what hidden ices were waking up under sunlight for what may have been the first time in ages. For that, astronomers had to do something harder. They had to break its light apart. Before we get to that chemistry, there's another piece of the rising tension you need to feel. This comet was moving fast, very fast. Hubble measurements described it as the fastest visitor ever recorded moving through our solar system, around 209,000 kilometers per hour in the observations tied to that report, and around 250,000 kilometers per hour near its closest approach to the sun. Speed like that is not just a dramatic number. It is evidence. It tells you this object had been roaming for an extremely long time. Gravitational nudges over ages can build a story into an orbit. Every star it passed, every distant encounter, every silent mile between systems helped shape the path that finally crossed ours. So now picture the full scene. A tiny nucleus, perhaps only a few hundred meters wide, maybe a few kilometers at most, wrapped in a much larger cloud of gas and dust, racing through the inner solar system faster than any visitor we had seen before. Mars missions strain to catch it. Hubble tries to pin down its size. Teams on Earth recalculate its route. And somewhere behind all of that sits the same haunting question. Where did this thing come from? Hubble helped sharpen one part of the answer while making another part stranger. Its observations suggested the solid icy core could be as small as a few hundred meters across, though the upper limit stretched to about 5.6 kilometers. That is a wide range, but even the upper end is not giant. The striking part was not just the size of the nucleus. It was the dust and gas around it. Hubble saw a teardrop-shaped cocoon of dust and signs of a tail. The coma was enormous compared with the likely size of the nucleus. That means a relatively small body was throwing off a huge amount of material. In simple words, this thing was lively. Why does that matter? Because comets reveal themselves by what sunlight pulls out of them. The warmer they get, the more buried ice can turn to gas and escape. Gas drags dust with it. The coma swells, the tail grows. Each changes a clue about the object's surface, its deeper layers, and the chemical mix it carried across the stars. In other words, the closer 3I/ATLAS came to the sun, the more it began to confess. But here is where things take a strange turn. The closer it came, the less this felt like a simple repeat of Borisov. Some features looked familiar, others did not. Scientists were seeing something comet-like, yes, but not comfortably ordinary. Even before the most dramatic chemistry results arrived, there was a sense that this object had formed in conditions unlike the ones that shaped most of the comets we know from our own system. That is the kind of detail that can change the whole meaning of a story. Because if an interstellar comet looks too much like ours, that is still valuable. It suggests other star systems make similar ingredients. But if it carries a mix that points to a very different birthplace, then suddenly it is more than a visitor. It is a sample from another kind of cosmic neighborhood, a message in ice. And this is a good moment to ask you something. If you knew an object had been drifting for billions of years before anyone on Earth ever noticed it, what would you want to learn first? Its chemistry, its age, its origin star, or just whether objects like this are common and we have been missing them all along? Hold that thought, because the next part of this story is where a moving dot became something much bigger. By late October, 3I/ATLAS reached its closest point to the sun, around 203 million kilometers away, just inside the orbit of Mars. This was the hottest moment of its passage, the point when solar heating would push the most material off the comet's surface. Brightness peaked. Activity peaked. Every useful instrument that could still track it was trying to collect one more piece before the chance closed. Then it curved away. And that is when one of the most powerful observatories ever built stepped in with a new kind of vision. The James Webb Space Telescope did not just take a prettier picture. It did what Webb does best. It read the invisible story hidden in light. Using its mid-infrared instruments, Webb looked at 3I/ATLAS after it had already swung around the sun and was heading back out. Those observations revealed something no interstellar visitor had ever shown us directly before. Methane gas. Not guessed, not hinted, detected. That discovery hit hard for a reason. Methane is volatile. It turns from ice to gas easily. If methane was still buried inside this comet until sunlight reached deeper layers, that means parts of the object had been protected for a very long time. Webb's data suggested the methane had not been sitting exposed near the surface all along. It had been hidden below the top layer and only started venting once the sun's heat reached farther in. In simple terms, the comet had a sealed memory inside it, and the inner solar system had just forced it open. Webb also found that the comet was unusually rich in carbon dioxide relative to water compared with typical comets from our own solar system. That is the kind of result that makes researchers sit up straight. It points to a different formation environment, a different chemical history, a different cold place around some other star, or perhaps at an extreme distance from that star, where ices and gases settled in a mix we do not often see here. The more scientists studied it, the more 3I/Atlas looked less like a tourist and more like evidence. Evidence of what? That is the core mystery. Evidence that planet making and comet making around other stars may produce objects very unlike the ones we grew up studying. Evidence that the galaxy may be full of icy wanderers with chemistries our models do not yet fully capture. Evidence that our solar system is normal in some ways and unusual in others. We still do not know which possibility will win. If you enjoy stories like this is exactly why the next discovery will matter so much too. 1 interstellar visitor is a marvel, 2 is a pattern beginning, 3 starts to feel like the edge of a larger hidden population. And the next one could be the object that tells us whether 3I/Atlas was rare or whether we have only just learned how to notice what has been passing us all along. Webb's measurements also showed a sharp drop in gas production as the comet moved away from the sun. That part was expected. Less heat means less active ice. Water shuts down quickly compared with more volatile materials. But in the context of 3I/Atlas, even the expected behavior was useful. It told scientists they were watching a real physical process unfold in layers. The sun had heated the crust, then reached deeper regions. Then the activity began fading as distance increased. This was not a static relic, it was a changing object, revealing different parts of itself as conditions changed. Imagine taking a block of ancient ice from a locked room and warming it inch by inch until different buried scents begin to escape. That is a crude picture, but it helps. The comet was not giving up all its secrets at once. It was peeling open. First one signature, then another. First the outer behavior, then the deeper chemistry. First the image, then the fingerprint. And still, that did not end the mystery. It sharpened it. Some researchers suggested its chemistry pointed to a very cold birthplace, colder than the regions that made many of our own comets. Others explored what that might mean for the kind of star it once orbited or the zone of a planet-forming disk where it formed. There was even discussion about whether it could be older than any comet we have ever studied, perhaps billions of years older than our solar system itself. That idea is still tied to uncertainty, but even the possibility is staggering. You are not just looking at old ice. You may be looking at matter shaped in a very early chapter of the galaxy. That is when the emotional center of the story changes. At first, this is a chase. Then it becomes a confession. Then, suddenly, it feels like contact of a different kind. Not contact with life, not contact with a machine, contact with another place, another history, another chemical world that came to us instead of us going there. Still, not every dramatic detail around 3I/Atlas pointed in the same direction. Some observations looked familiar enough to remind scientists that comets, even interstellar ones, can still follow natural rules we already understand. Cyanide-related compounds and nickel vapor, for example, are not proof of anything bizarre on their own. They can appear in ordinary comet chemistry too. This is an important line to hold. In stories like this, the temptation is always to let every odd feature become a giant leap. Real science works differently. It sorts, it compares, it refuses to be impressed too quickly. That brings us to the sharpest argument surrounding this visitor. A few voices noted that parts of its path looked statistically unusual and worth watching closely. The most famous of those voices, Avi Loeb, pointed to features of the trajectory and geometry that he felt deserved extra scrutiny. He did not claim proof of technology, he argued for attention. Mainstream researchers, however, remained firmly with the natural explanation. To them, 3I/Atlas looked like what you would expect from a galaxy full of planetary systems, throwing out icy bodies over billions of years. A strange path is not the same as an artificial one. An unusual number is not the same as evidence of design. This disagreement matters because it reveals how science behaves under mystery. One camp says, be cautious and do not outrun the data. Another says, do not become so cautious that you ignore anomalies. The healthy middle is uncomfortable. It writes down the odd detail, then waits for more objects. If the next interstellar visitor shows similar traits, the conversation changes. If the one after that does too, it changes again. But one object alone cannot carry a claim that large. So where does that leave the story? Right at its emotional peak. On one side, we have the most grounded explanation. Planetary systems throw out debris all the time. Giant planets scatter smaller icy bodies during the violent years of formation. Some fall inward. Some get captured into distant reservoirs. Some are launched into interstellar space forever. Multiply that across hundreds of billions of stars, and the Milky Way should be full of wandering exiles. By that logic, 3I/Atlas is not impossible at all. It is expected. Rare to detect, yes. Rare to exist, probably not. On the other side, we have a deeper discomfort. If these objects are expected, why have we only just begun to find them? How many are out there right now, too faint for us to notice? How much material moves between star systems without any civilization ever seeing it? And if our first small sample already includes bodies this different from one another, what does that say about the variety of worlds that exist beyond the sun? This is the part nobody can answer neatly yet. Not because the science failed, but because the science is just getting started. By the time 3I/Atlas was arcing away from the sun, scientists were already shifting from observation mode to interpretation mode. That is when the expert reactions became almost as fascinating as the comet itself. Some focused on its size, some on its chemistry, some on the tracking challenge, some on the big population question. Because if we can now detect interstellar objects more reliably, every one of them becomes both a case study and a data point. A sample of one is mystery. A sample of many becomes a map. One reason the Mars observations mattered so much was practical, not just poetic. Seeing the comet from Mars gave teams a different geometry and a new kind of tracking experience. That matters for future planetary defense work too. Not because this object threatened Earth. It did not. But because learning how to coordinate spacecraft across the solar system to follow a fast-moving body is exactly the kind of skill you want before a more urgent target appears. In that sense, 3I/Atlas was also a rehearsal, a test of speed, teamwork, and flexibility. You can hear the shift in tone when agencies talk about it. There is excitement, but also preparation. ESA has already tied part of this story to its future Comet Interceptor mission, a mission designed to wait in space for a suitable target. That idea suddenly feels much more urgent in a world where interstellar objects are no longer pure theory. The Vera Rubin Observatory is expected to transform discovery rates too, scanning the sky with a power past surveys did not have. Many astronomers think it could start finding interstellar visitors more often than we once imagined. If that happens, 3I/Atlas will not remain an outlier. It will become the object that taught us how to respond. And maybe that is its quiet legacy. Not just what it was, but what it forced us to become. Think of the graduate students and early career researchers who were thrown into this story. One day they were studying ordinary comet behavior, survey pipelines, orbital mechanics, or infrared spectra. The next day, they were helping read the chemical trace of matter from another star system. The work they did in those few urgent months will likely echo for years. Papers will keep coming. Old data will be reprocessed. Models will be updated. Arguments will continue. The object itself will be long gone, but the science it triggered will keep moving. There is something deeply human in that. We are a species that often learns in a rush. We build our machines slowly, then history comes flying in fast. Suddenly, the schedules are torn up. The cameras are repointed. The experts stop sleeping much. And then, for a very brief window, all the preparation of decades meets a single, unrepeatable event. That is what happened here. Hubble, Webb, Mars orbiters, ground observatories, all of them converged on one cold wanderer because everyone understood the same basic truth. This was not coming back. If you were one of the scientists on that team, how would that feel? Imagine knowing that every measurement matters because the object is already leaving while you're still collecting the data. Imagine noticing a strange chemical ratio, or a burst of methane, or better constraint on the size, and realizing no future mission will get to circle back and check your work up close. There is no redo. There is no landing attempt. There is only this pass and whatever your instruments can catch. That pressure can do something beautiful. It can strip science down to its most alive form. Not dry facts on a shelf, but people trying to read the universe before the page turns. And the page did turn. After its close brush with Mars and its hottest swing around the sun, 3I/Atlas kept going. It passed Earth at a much greater distance, still watched but already fading. It later passed near Jupiter too, but not close enough for that giant world to capture it. That point matters. Even the strongest gravity well among the planets could not claim this visitor. It remained what it had always been, a passerby. By early 2026, follow-up studies were still extracting meaning from its changing activity. By then, the comet was dimming toward the limits of what even major telescopes could follow. Eventually, it would slip beyond easy detection entirely. Not destroyed, not lost in the dramatic sense, just gone from our reach. There is a strange ache in that idea. The comet still exists. It is still moving. Somewhere beyond the easy grasp of our instruments, it is continuing the same journey it began long before Earth had oceans like the ones we know now, long before human beings, long before every empire, every language, every telescope. It entered our awareness for a blink, gave us a little of its chemistry, a little of its shape, a little of its motion, and then moved on. So what did it really mean? At one level, the answer is simple. It proved again that our solar system is not sealed off. Material moves between stars. Comets and rocky bodies are not locked forever to the places that formed them. Worlds throw pieces of themselves into the galaxy. Those pieces travel. Most drift unseen, but every so often, one crosses another system at the exact moment someone there is able to notice. At another level, the meaning is bigger. 3I/Atlas was a reminder that astronomy is no longer only about looking far away. Sometimes the galaxy sends a fragment of itself to our door. We did not travel to another star. Another star system sent us a clue, and because our technology had finally reached the right stage, we were able to catch that clue, not just from Earth, but from Mars too. That changes how you think about exploration. We are not only voyagers, we are also witnesses. There's also a humbling lesson here about scale. For nearly all of human history, the stars were symbols. They were distant lights, stories, gods, maps, wishes. Then science taught us they were suns. Then spacecraft taught us that planets orbit many of them. Then spectroscopes taught us we could read atmospheres from light. And now, in an age that still feels young, we are reading the chemistry of matter that formed around another star and drifted into our neighborhood. The distance is still enormous. The mystery is still overwhelming. But the wall between here and there is not as solid as it once seemed. That does something to the imagination. It makes the galaxy feel more physical, less like a backdrop, more like a place where exchange happens. Matter travels, energy travels, light travels. And sometimes, very rarely, the leftovers of other solar systems come close enough for us to inspect. This is why the broader scientific community cared so much, even beyond the immediate thrill. The chemistry of an interstellar comet is a test of our models. If it formed in a colder environment, what kind of star did that? If its carbon dioxide to water ratio is so unusual, what does that say about where ice is settled in its original system? If methane stayed buried until deep heating occurred, what does that tell us about layering and surface processing over immense spans of time? These are not narrow questions. They connect directly to how planets form, how disks evolve, how icy bodies are stored, and how often systems throw material away. And once you start asking those questions, Earth feels smaller in the best possible way. Not unimportant, just placed in a larger story. Maybe that is why this event struck such a chord. It mixed technical excellence with something almost emotional. The repointing of Mars spacecraft was a feat of planning. Webb's methane detection was a triumph of instrumentation. Hubble's size estimate was careful, disciplined work. But underneath all of it was something older than science itself, wonder. That old human shock at realizing the universe is both stranger and more connected than we thought. There's another reason this story lingers. It carries a kind of perfect timing that feels almost unfair. Had 3I/Atlas come through centuries ago, nobody would have known. Had it passed much farther out, even our modern surveys might have missed it. Had the Mars geometry been different, the most dramatic imaging opportunity might never have happened. The event was real science, not fate, but it still feels improbably well-timed. The right object, the right era, the right tools, the right alignment of attention. History often looks inevitable after the fact. In the moment, it is usually a chain of fragile chances, and this one leaves behind an unresolved promise. The next interstellar visitor will arrive in a world better prepared than the one that met this comet. Survey systems are improving. Follow-up networks are faster. Space agencies now have a clear proof that retasking missions across the solar system can pay off. Astronomers know more about what to look for in the chemistry. Debate has already sharpened the questions. In that sense, 3I/Atlas did more than visit, it taught. It taught us that even a dim, fuzzy target can become the center of global attention when the orbit says interstellar. It taught us that a Mars mission can become a deep space lookout with the right timing. It taught us that infrared fingerprints can reveal hidden methane in a chemical story that does not fit comfortably with local norms. It taught us that small, icy bodies can carry enormous meaning. And it taught us, perhaps most of all, that the galaxy is not a museum behind glass. Pieces of it move through our neighborhood. The most haunting part may be this. Somewhere out in the dark now, beyond the easy reach of our eyes, 3I/Atlas is still carrying secrets we did not get to unlock. We know more than we did, but not everything. We do not know its home system. We do not know what planets may once have shared its birth environment. We do not know the exact moment it was thrown into exile. We do not know how many stars it drifted past before it found ours. We caught a chapter, not the whole book. But maybe that is enough. Maybe that is what makes the story powerful. The universe does not owe us complete answers. Sometimes it gives us a passing clue and asks whether we are paying attention. In 2025, we were. Scientists in Chile found the first sign. Teams around Earth confirmed the impossible path. Mars orbiters turned their cameras. Hubble sharpened the silhouette. Webb read the chemistry, then the object departed, leaving us with data, debate, and a wider sense of where we live. And that central question still hangs there, stronger than ever. What was this ancient traveler really telling us about the worlds beyond our own? Not in fantasy, not in slogans, in chemistry, motion, and time? Was it an extreme example of a natural class we are only beginning to sample? Was it a sign that other systems build icy bodies in ways more varied than our models predict? Was it simply the first clear taste of a population the Rubin era will soon reveal in large numbers? The answer may arrive with the next visitor, or the one after that.